resistivity of intrinsic silicon at 300 degree Kelvin. So it is mu n, it is the mobility of electrons. It is 1350, it is the bulk mobility of electrons, that is centimeter square per volt second. And mu p is the whole mobility, it is small as compared to the mobility of electrons. 480, yeah. Oh, you cannot see this? Okay. You can see now, no? Uh-huh. Now you can see this. Okay. Now you can see, no? Okay. So here is see it is the thermal equilibrium concentration of electrons, that is N0, that is equal to P0 is the whole concentration, and that is equal to intrinsic carrier concentration. So sigma I, that is the conductivity of intrinsic silicon, that is equal to Q. Q is the elementary charge plus mu n plus mu p into Ni. So if you put the different values of the quantities, you will get the resistivity is approximately equal to 4.39 into 10 to the power minus 6 ohm centimeter inverse. So the resistivity, that is the reciprocal of the conductivity, it is on the order of say 3 into 2.28 into 10 to the power 5 ohm centimeter. So this is one important uh, actually problem regarding intrinsic silicon, how to calculate the resistivity as well as this conductivity of this material. You know that the drift, there are two mechanisms by which uh, carriers flow inside the semiconductor. One is the drift mechanism, another is the diffusion mechanism. So if we apply an electric field across the semiconducting materials, carriers will be accelerated due to the applied force, that is equal to charge times electric field. And this kind of motion is called the drift motion of carriers. So the motion of the carriers under the influence of an electric field is called the drift motion of carriers. So if we apply an electric field across a semiconducting material, an electric field will be established, and that will exert force on the charge carriers. And under the influence of these charge carriers, the carriers will move from one region to another region. Uh, More specifically, holes will move in the direction of the electric field, while electrons will move in the opposite direction. Okay. So if we designate this drift velocity by Vd, Vd is equal to some quantity that is called the mobility into electric field. That means we can say that the mobility is the drift velocity of carriers per unit electric field. But mobility is not a constant quantity. It is a function of many parameters that I'll discuss now. Okay. And you know that apart from this drift motion of carriers inside the semiconductor, there is also diffusion of carriers. Diffusion means when these charge carriers move from a region of higher concentration to a region of lower concentration. That means whenever there is a concentration gradient, carriers move from a region of higher concentration to a region of lower concentration. That is called the diffusion. So there are two mechanisms of flow of charge carriers. One is drift, another is diffusion. So I'll actually define the mobility, that is the drift velocity of carriers per unit electric field. So now I shall discuss the effects of temperature and doping on mobility. So here you see uh, the variation of mu, that is the mobility of say electrons with respect to the temperature. Both are plotted in log scale, so it is a log plot. So when the temperature is low, so mobility increases with increasing temperature, and at that time the impurity scattering is a dominant mechanism. Uh, Impurity scattering means you know that in a doped semiconductor there will be ionized charges. For example, if we consider N-type material, so there will be ionized donors inside the semiconducting material. So if one electron comes nearer to the donor atoms, it will be attracted because of the negative charges on the electron and positive charges on the donor atoms. And if electron finds it is nearer to another electron, then it will be repelled. So this kind of motion, attraction or repulsion will take place when the temperature is low. So, uh, at a very low temperature, there will be a dominant of the Coulomb attraction or repulsion depending on the polarity of the charges. So, therefore, as temperature decreases, there will be a more probability of this type of scattering events by which the mobility will be degraded. Therefore, for a low value of temperature, you see mobility drops. But as temperature increases, the carriers will be thermally excited, and the Coulomb attraction or repulsion will is unlikely to affect their motion. Therefore, it will increase the mobility of the carriers, and you see that the rise in mobility follows this T to the power 3 by 2 law. So it is a nonlinear variation of mobility with temperature. But at a higher temperature, there is another important scattering mechanism that is called lattice scattering or phonon scattering. So at a higher temperature, there will be vigorous vibrations of the crystal lattice, and it will encounter with the free charge carriers, and therefore the mobility will again will be degraded, and that is why at higher temperature, another scattering mechanism that is called the lattice scattering mechanism, or you can say this is the phonon scattering. Phonons are nothing but lattice vibrations. So therefore, again, mobility will fall following this T to the power minus 3 by 2 law. So in between there is a maxima of mobility. So at an intermediate temperature, when both the scattering mechanisms will be less pronounced, and at that time mobility will attain its peak value. So it is the variation of mobility with variation in temperature. So corresponding to each scattering mechanism, we can assign a mobility to the carrier, and in general there will be a number of scattering mechanisms present in the semiconductor. So therefore, in order to calculate the overall mobility of the carrier, we can use this Mathiassen's rule. That is, mu is the overall mobility of carriers, and 1 upon mu, that is equal to 1 upon mu 1. So mu 1 corresponds to a particular scattering mechanism, say it is the impurity scattering, and 1 upon plus 1 upon mu 2. Mu 2 could be the phonon scattering, or in case of alloy semiconductors, you can say that is 1 upon mu 3, that is the alloy scattering, and so on. So it resembles like a parallel combination of resistances. So you know that the lower mobility actually will determine the overall mobility. Like in case of parallel combination of resistors, what will happen? The lower value of resistance actually determines the overall or the equivalent resistance. Here, the same thing follows. That means the lower value of mobility will determine the overall mobility of the carrier. So there is a variation of both electron and hole mobility with carrier concentration. So mu n refers to the electron mobility, mu p refers to the hole mobility. You see, it is the doping concentration. It varies from 10 to the power 14 to 10 to the power 19. So as the doping concentration increases, the mobility, both electron and hole mobility, drops down with increasing doping concentration. It is obvious because a large number of dopants inside the semiconducting material means large number of ionized charges available. So there will be more amount of impurity scattering, and therefore the mobility degrades with the increasing amount of dopants or impurities. So next thing is here. This is the drift velocity Vd. Vd is the mobility times electric field, and J is the current density. It is sigma times the electric field. Here you see the variation of drift velocity of carriers with the electric field. So for low value of electric field, Vd is almost proportional to electric field. That is why you see here the linear relationship, means Vd increases linearly with electric field, and after some value of E, the relationship becomes sublinear. It is less than the linear projected or extended curve. The variation will become slower, and ultimately it saturates when electric field exceeds 10 to the power 5 volt per centimeter square. So this is actually the variation of uh, drift velocity with respect to the electric field. So under such situation, what happens? Why the saturation takes place? Although the carriers gain energy from the electric field, the rate at which carriers gain energy, it will release energy at the same rate in terms of this phonon vibrations or emission of phonons. It could be acoustic phonons, means phonon vibration, or it could be again depending on the frequency, it could be optical phonons also. So if there is a very high amount of energy which carriers can gain from the electric field, and the energy, excess amount of energy will be released by emission of these optical phonons. So therefore, this saturation velocity is maintained. Means although the electric field increases, there is no increase in the velocity of the carrier. This is actually can be accounted for the fact that the rate at which carriers gain energy from the electric field will be same as the rate carrier will lose or release energy to the crystal lattice. Okay, so this is all about this mobility, and as I told you, uh, there are two mechanisms of current flow. One is drift and another is diffusion. So here you see inside a semiconductor, the current density has four components. First component is related to the drift of electrons, q n mu n into ex. Second component is the drift of holes, that means qp mu p into ex. Next one is the diffusion component of electrons. dn is the diffusion coefficient, q into dn, and dn dx, it is the gradient of electrons, and minus q dp dp dx, it is actually contribution of the whole diffusion current. So in a semiconductor, we know that there are two free charge carriers. One is electron, another is hole, and there are two mechanisms of current flow. That is, one is diffusion, another is drift. So if we combine all the combinations, that means we can get four components. Therefore, in a semiconductor, the current density has four components: two for electrons, two for holes, and one for the drift mechanism and another for the diffusion mechanism. And it is very important relationship. It is called the Einstein's relationship, d by mu equal to kt by q. So it holds good for both electrons and holes. So it is all about the overview of the syllabus, and another topic I'll tell you. Can you see in this slide? Okay, so here is excess carriers in a semiconductor. That means we already considered that the semiconductor is under thermodynamic equilibrium, and when semiconductor attains this equilibrium condition, there will be equilibrium electron concentration as well as equilibrium hole concentration. But if we actually generate the carriers in excess of the equilibrium carrier concentration, and that is called the excess carriers. So excess carriers can be generated in a semiconductor by various methods, such as optical excitations, high energy particle bombardment, or injection of carriers by bias. So if we shine a semiconductor with some radiation, the semiconductor will absorb energy from the radiation, and it will actually generate these electron hole pairs. So condition is that the h nu, that is the energy of each quanta, or the photons of the radiation, must be higher than the band gap of the material. Otherwise, uh, mm, uh, all radiation will pass through the semiconductor. That means in such a case, the semiconductor will behave as a transparent material to when it is exposed to radiation. So condition is that when the h nu or the uh, amount of energy of each photon is greater than the or equal to the band gap of the material, the semiconducting material will absorb its energy. So in case of excess carriers, what will happen? The conductivity will be changed. So therefore, sigma is the new conductivity, n0 is the equilibrium electron concentration, and delta n it is the excess electrons generated by say optical excitation. Q into mu n plus p0 is the actually uh, equilibrium value of the whole concentration. Delta p is the excess whole concentration due to some excitation, maybe optical excitation. Q into mu p. So as you know that excess carriers will be much higher as compared to the equilibrium electron concentration. Therefore, we can say delta n is much higher than n0. So sigma has two parts. One is actually sigma 0. It corresponds to the thermal equilibrium value plus delta sigma. It is due to say photoconductivity due to photons. So here you can see this optical absorption of the photons by a semiconducting material. So here a photon is incident and that photon energy is greater than the band gap of the material. Therefore, the semiconductor absorbs photon, and by absorbing the photon, uh, one electron in the valence band can make a transition to the conduction band. So it is indicated by this figure A. So one electron in the valence band is promoted to the conduction band at a higher state. Now it is excited here, so it wants to thermalize and actually releases energy in the form of phonons. So there is B is the thermalization. And next, it makes another transition from conduction band to valence band. So thereby emitting a photon of energy h nu. It is obviously this h nu is actually lower as compared to the incoming photons because this energy difference is equal to the band gap. So these are the possible mechanisms by which semiconductor material interacts with the radiation. So there is, if you go through this, how absorption takes place in a semiconducting material, it follows some exponential law, that is Ix, it is the intensity at a point x, I0 is the uh, intensity when the radiation is incident at the surface of the semiconducting material, and it is actually follows this exponential rule law e to the power minus alpha x as this photon moves inside the material. There is a probability of getting absorbed, and it follows this exponential rule. Alpha is called the absorption coefficient. So it is graph shows the variation of absorption coefficient with energy. You see, it is very important that whenever energy of the photon is less than Eg, so their absorption is very less, almost negligible. Because at that time the semiconductor behaves like a transparent material. So radiation passes across the semiconducting materials through the semiconducting material without getting absorbed. And if the photon energy exceeds Eg or equal to Eg, then there is a sharp rise in the absorption coefficient. That means almost most of the photons will be absorbed inside the material. So this is an important characteristics. And there are some excitation mechanisms, type of luminescence, and the examples. So this general property of light emission is called actually luminescence. You know that electron-hole pairs are generated in a semiconductor by optical absorption or by any other means, and the excited carriers fall into the equilibrium state, and due to that process, light will be emitted. And this general property of light emission is called luminescence. So here there are three different kinds of excitation mechanism. One is photon absorption, and the type of luminescence is called the photoluminescence. And example is the fluorescent tube. Next is the high energy electron bombardment, that is called cathodoluminescence. And you know that CR2 tube, cathode ray tube, where electron gun is used, and it is passed through the electric and magnetic fields, and it actually displays on a screen. So then in case of light emitting diode, excitation mechanism is we are injecting current into the sample. Means this diode is forward biased and current is injected into it, and this type of luminescence is called electroluminescence because we are injecting current. And example is the PN junction light emitting diode. So this is the actually how to generate excess carriers, and their properties and different kinds of luminescence. And you go through this direct recombination of electrons and holes, as I explained with reference to the direct bandgap semiconductors. You know that the both the top of the valence band and bottom of the conduction band occur at the same value of propagation constant k. So therefore, whenever an electron in the conduction band wants or makes a transition to the uh, vacant valence band, it requires no change in momentum, only there will be a change in the energy, and the excess amount of energy will be released with the emission of photons. So this is how the recombination of a EHP pair takes place. So there are some mathematics as well. So you can go through it. And I think tomorrow is your exam. Oh. So okay. Okay. So you prepare for the exam, and from 15th, I think your end semester exams. Okay. And then you please contact with the your course coordinator, Shampa ma'am. In case of any difficulties, you can contact her. And your general coordinator is Shumitra ma'am. And if in case of any other problem, if they cannot solve it, then you contact me. Okay. Which one? Okay, okay. So I will send it to the group along with your email. Okay, okay. Then I'll send you separately to your email. Okay. Okay. Okay.